Chapter 3, Engineering Analysis Disciplines in ASTROS. This slide shows the difference between ASTROS and NATRAN in engineering analysis disciplines. For structural model, both ASTROS and NATRAN they use finite element method, and the element C-quad4, C-quad3, C-bar, C-rod, C-elast, column M1, column M2, those elements are identical between ASTROS and NATRAN. For aerodynamic model, ASTROS use zone 6 method for subsonic flow, zone 7 method for supersonic flow, Z-tran for transonic. In NATRAN, they have a double lattice for subsonic flow, zone 51 for supersonic flow. They have no unsteady aerodynamic method for transonic aerodynamics. Zone 6 is a higher order unsteady panel method than double lattice, because DRM is a low order unsteady panel method. Zone 51 is a subset of zone 7 for lifting surface modeling only, and so zone 51 cannot model bodies. Okay. For buckling panel and column buckling analysis, ASTROS use so-called local approach using analytical buckling equation for panel buckling, column buckling, and whole stiffening panel bay buckling constraints. NATRAN uses the global approach by solving the eigenvalue of ASAT stiffness matrix. To capture stiffener buckling crippling mode, NATRAN requires detailed modeling of the stiffener by plate elements, whereas ASTROS uses P-bar ST to model the composite stiffener. So ASTROS use P-bar ST to model the stiffener, and this one is not available in NATRAN. So ASTROS evaluate stiffener crippling constraint using one edge and no edge free analytical buckling equation. For factor solution, ASTROS use G method and NATRAN use PK method. Those methods in most cases give you the very close result. The trim analysis, both ASTROS and NATRAN use the so-called direct method by combining the ASAT stiffness and ASC matrices, then solve coupled equation in the ASAT. For optimization algorithm, ASTROS using M dot and dot, and the dot in NATRAN version 2007, and after 2007 they use ADS. M dot and dot are commercial software from Vanderplot R&D Inc. ADS is in public domain. So both M dot and dot using so-called gradient-based optimization, which requires the sensitivity analysis. For engineering analysis disciplines in ASTROS, we have a static analysis design of structure subject to time invariant loads, which we solve this equation, and where the mass matrix MGG is used to perform so-called inertial relief for a free structure. Modal analysis and ASTROS use lentils and inverse power and given method to solve this eigenvalue problem. For flutter analysis, and it use the G method to solve this flutter equation, where S is the Laplace variable, and MHH is the generalized mass, and the BH is the generalized damping, KHH is the generalized stiffness matrices, and the QHH is the generalized area and forces. and static area elastic and trim losses. So it can solve the trim equation and produce the trim loads, and then this trim loads are applied to the structure, and then you can impose a stress strain evaluation, which you can specify principal stress strain and the fiber transverse strain. And panel buckling, beam buckling, stiffening, crippling analysis. We solve this and we use this analytical solution, and we solve panel by panel to evaluate the panel buckling constraints. The static analysis is activated by the static case control command. So you can specify statics, and map equal to 1. It refers to a set of a force and a moment cost. And meanwhile, you can impose stress constraint. So the stress constraint refer to the decon VMM, then decon TWM. This is used by May's stress equation. This is inside Wu stress equation. So this the structure before optimization. This the optimized structure. So ASTROS takes 11 iterations to achieve optimized structure. Meanwhile, satisfy all the stress constraints under this static loads. So you can see you can reduce the weight from the initial weight to achieve a minimum weight solution. And so the static case control command, it can refer to a force and force 1, or moment and moment 1, P-load 2, P-load 4. This is for impose the gravity force. This the temperature induced stress. And modal analysis is activated by the modes case control command. So you can impose static two static loads, and also you can say modes, and the decon S refers to decon FRQ. This imposes the natural frequency constraint. So that the lowest natural frequency must be greater than 4 hertz. Okay, and meanwhile, the method you refer to AGCON. Then we simply say we want to use Lanczos solver and to solve this eigenvalue problem. So it takes about if you don't impose the natural frequency constraint and the optimized the structure takes about 11 iteration, and so the lowest natural frequency is about 3.1 hertz, and so this the optimized structure without frequency constraint. With frequency constraint, it takes about 14 iteration, and the natural frequency, you can see the first natural frequency is almost satisfied the constraint. So it's 3.999. So it satisfies the lowest natural frequency to be 4 hertz. And the flutter analysis is activated by the flutter case control car. So you say flutter, and Blackcon refer to a flutter car, and the flutter car also refer to fixed and then car. And this is a non-match point flutter analysis. So at a given density, we list out several velocities. So the highest velocity in this case is about 18,000 inch per second, and we can impose the flutter constraint called decon flut and 10999, and meaning, and for the from 0 velocity to 12,300 inch per second, the damping of all modes must be less than 0.015. Okay, so showing here, if we without imposing flutter constraint, and it took 6 iteration to obtain a converged solution, because we have 2 static loads condition to impose the stress constraint. But if with a flutter constraint, it took about 20 iteration. The weight is a little bit higher than the one without flutter constraint. And so the case control command flutter, and flat count equals integer. This integer is the ID of the flutter count. And the flutter count, you can refer to 2 type of match point flutter analysis and 2 non-match point flutter analysis count. And also you can refer to a TAB DMP1 count to include modal damping in the flutter equation. Also, you can refer to the CONAM list card to list out set of CONAM 1 and CONAM 2 to add mass into the flutter equation. Also, it refers to set 1 card. In the set 1 card, you list out the mode index, and those modes will be excluded from the flutter analysis. Also, you can output you can specify a plot VG card to output the data to that can be used to create a VG and VFF diagram. And then you can refer to a flat card can refer to a plot fluid card, and you can do the flutter mode and animation. All those cards also refer to MKLZ card. MKLZ card is to create the ASC matrix. So this is the sample flutter input card. You have a flutter card, and you specify it's an anti-symmetric flutter analysis, and then this one refer to the fixed ATM card. In the fixed MTM, this is the match point flutter analysis card, and then you list out the altitudes from below sea level to 5,000 feet, and the MList entry 1, 2, 3 refer to a set 1 card with ID 1, 2, 3. So you list out 1, 2, 3. So the first 3 modes will be excluded from the flutter analysis. And this is a typical flutter analysis output. You print out the velocity and the density and altitude, and for each mode you list out the damping, the frequency, and the reduced frequency. And then after that, you will find out the damping cross 0 condition, and you interpolate, say that the altitude will be between 30,000 to 25,000 feet, so it's 28,000 feet, and which the speed is about 900 feet per second, and the frequency is 5.4 hertz. This is the dynamic pressure. This is the density. And in addition to 0 damping condition, the flutter module will also add half percent damping up to 4% damping. So if you have if you have 3% of a structural damping, the flutter altitude become a negative, because this is a very shallow crossing. With a little bit of structure damping, it can suppress the flutter instability. And also, you can generate the VG diagram using the plug VG car. And in the plug VG car, you can specify file name to store the VG and VF diagrams. And however, the actual name is VG.I. I is the iteration index during the optimization. And this file can be used by the program called vgplot.exe to generate the VG and the VF diagram. The vg.exe can be found in the miscellaneous folder. And to perform static error elastic and trim analysis, we use the SARROW case control command. So we specify SARROW, and the trim is asymmetric trim condition. We have 5 trim cases. Each trim cases will create a trim load, and then we impose the stress constraint, and also we can impose the buckling the aileron effectiveness constraint. Also, you can impose the buckling constraint under those 5 trim loads. So as we'll simultaneously apply those 5 trim loads on the structure, and the structure must satisfy those stress constraint and also the aileron effectiveness constraint. And also, if you include a buckling constraint, you also will satisfy the buckling constraint. And the trim motor car specified by you have a trim car, and it's referred to by the case control command SARROW. Trim equal to K, and equals to K, and K is the index of the ID of the trim car. A trim car also referred to MKLZ car, and MKLZ car refers to a trim flood car. And in the trim flood car, you specify the mean flow condition, like the angle attack, the control surface deflection, and trim type. QDP is the dynamic pressure, and the trim type, you have if a blank, the trim equation is specified by the support car. In the support car, you have 3 rigid body mode. Then you have 3 trim equations. Rho is anti-symmetric rho, 1 degree of rho trim equation. Lift is a 1 degree lift equation. And pitch, you have 2 equation. One is pitch, one is lift. So it's a 2 degree trim equation. After that, you have a label, and the label you specify it refers to, you can specify an angle tag or a control surface label, and also you can specify the acceleration along x, y, z direction, like NZ, and also, and the value, you have 2 choices. One, you specify a real value. That means for this trim variable, the value is given, or you can put a free, and then so for this trim variable is unknown, and which was solved by the trim module. And the typical trim output, you will list out the stability derivatives. The thick can, meaning it is the mean flow condition which specified in the trim flood car, and the angle attack alpha is a per degree, and you will list out the rigid and the flexible. Okay. For pitch rate, we call Q rate. It is a non-dimensional quantity, and per QC over 2V. Also, you have rigid value. You have a flexible value. For control surface, for example, this is an elevator. Is per degree. You also have the the rigid and the flexible value. Those are all stability derivatives. The trim module will use those stability derivatives and to project the trim solution to satisfy the trim equations. And so you will output the trim solution, and the load factor NZ is a given, is a user input. So I want to define satisfy NZ equal to 8, and another user input is a Q rate, which is a pitch rate. Then I have two unknown trim variable. One is angle attack, one is elevator deflection angle. So this is the flexible solution. This is the rigid one. And finally, I have a thick cam, which is a given. And ASTROS includes the zero geometry modeling, spline, and aerodynamic modules, support the flutter and trim disciplines in ASTROS. So we use so-called the CL7, body 7, to model a whole aircraft, and with the underwing engine nacelle. And also we have a 3D spline module to spline or map the structural modes onto the onto the aerodynamic panel model, and also map the aerodynamic forces from the aerodynamic panel model back to the structure grid. ASTROS adopts the steady unsteady aerodynamic method from 0, and so we have a Rho 6 for subsonic, Z-Trend for transonic, Rho 7 for supersonic, and Rho 7U for hypersonic. All zero aerodynamic method can model complete aircraft, including fuselage, lifting surface, and stores. National uses the DLM, the double lens method, for subsonic Mach number, and Rho 51 for supersonic Mach number. And both methods cannot model the complete aircraft. It cannot model the fuselage and the engine nacelle. Z-Trend can capture the transonic shock effect and the transonic flutter deep, where DLM and Rho 51 cannot, because of the linear potential equation theory. So this is a typical flutter boundary of a transport aircraft. If you use Rho 6, you do not capture the transonic deep. And if you use Z-Trend can capture this transonic deep. And without capturing the transonic flutter transonic deep, the optimized structure is prone to having flutter problem. So the Boxer card for aerodynamic modeling is identical to zero. So you use a CL7 to model the lifting surface. You use body 7 to model the body-like aerodynamic component. And then you have the AeroZ card to define the aerodynamic reference parameters, like the reference core, reference span, and the reference area. Use MKLZ card to generate the ASC matrices. All aerodynamic input cards, 07, body 7, are identical to 0. The transonic Z-Trend method is not available in ASTROS. However, the ASC matrix generated by the Z-Trend method in 0 can be directly imported into ASTROS using the entry save equals acquire in the MKLZ card to perform transonic flutter analysis. During ASTROS optimization, the ASC matrix is not loaded in the ASTROS runtime database because the ASC matrix sometimes is huge, and the runtime database, one database only can take 2 gigabytes. So so to avoid to having many runtime database during the ASTROS computation, we load the ASC matrix on a temporary external file called AGAG S0101 dot AICXX and so on. Those files will be deleted upon the completion of the ASTROS run. The G method in ASTROS and in ZERO are identical. All input cards associated with the flutter analysis using the G method are also identical between ASTROS and ZERO. A new input card called AddDam has been added into ASTROS. Why we need this card? The AddDam card adds damping to the damping of a specified mode computed by the G method to artificially stabilize certain flutter mode. The add damping card is normally used when the rigid body flutter mode is unstable. An unstable rigid body flutter mode is difficult to suppress by stiffening the structure. So therefore sometimes you need to add a lot of weight in order to suppress the rigid body flutter mode. Using the add damping mode to artificially suppress the unstable rigid body mode for a statically unstable aircraft can prevent ASTROS from adding large weight. Okay, and sometimes if the aircraft is statically unstable, the rigid body mode will be unstable, and so this statically unstable aircraft will be stabilized by a flight controller, but in ASTROS we don't have this modeling controller capability, so we artificially add damping to the rigid body mode to stabilize the rigid body mode, and then the flutter module only give the calculate the flutter condition of elastic mode. The spline module between ZERO and ASTROS are identical. We have an infinite place spline method called spline 1, beam spline method called spline 2. We have 3D spline using so-called thin place spline. The card name is called spline 3. The attach is a rigid body attachment, where spline 0 impose 0 displacement condition, and each spline card will refer to a second card to list out the structural grips, and also the panelist card to list out the aerodynamic box IDs. And also you can specify plug mode card to plug interpolated mode on aerodynamic model. Then you can save the spline matrix using spline M card, and you can change the spline matrix for force mapping using spline spline F card, and spline DOF card you can change the spline degrees of freedom of the structure model. MKLZ card generated unsteady aerodynamic AIC matrices. So define. So first you give ID, and you give a Mach number. You specify a method, and the method if the method is 0, and then for subsonic and supersonic and sonic they use zone 6, zone 7, and ZSAT. If the method equals 2 and the Mach number greater than 1, and you use zone 7U, the hypersonic aerodynamic method, then you have method equal to 3 and Mach number not equal to 1, you use the ZTRAD method. Okay, and the ID flood refer to a trim flood car. In trim flood car, you define the mean flow condition, and so the unsteady aerodynamic data are computed by perturbation about the mean flow condition, and the mean flow condition is specified by the angle tag and the control surface deflection, side slip angle, and so on. And this one you can save the AIC matrix, or you can acquire existing AIC matrix, and also you can say save equals add, This means you retrieve an existing AIC matrix and add a new reduced frequency to the reduced frequency list. Then you specify a file name, and to save or retrieve the AIC from this file. Then you list out the reduced frequency, and this reduced frequency is normalized. It's non-dimensional quantity. It is normalized by the reference core, half of the reference core, and also divided by V infinity. And IFC is the reference core defined in the arrow Z cup. And the value of the least reduced frequency, if it's not zero, if the lowest reduced frequency is not zero, and also we add a zero frequency into the list. So the first reduced frequency always hardwired to be zero. And also the reduced frequency can be, you can put a negative sign in front of the reduced frequency. That triggers the program to add a more Gaussian integration point for accurate numerical integration at high reduced frequencies. Okay. Because ASC matrix only contains the pure aerodynamic characteristics of the configuration, it is independent of the structure, therefore can be saved and repeatedly used for structural optimization. The AIC matrix must be recomputed when the aerodynamic panel model is changed, the Mach number is changed, the input card trim flood is changed, a new reduced frequency is specified. Then in this case you can say save equal to add. The steady background flow for the Z-chain method is changed. The AIC matrix can be reused even the structure finite model is changed. The spline input card is changed. All input card for flutter, trim, those analysis is changed. You can also you still can reuse the AIC. Reuse a previous saved AIC matrix can reduce the computational time. If the aerodynamic panel model is changed but a saved AIC is reused, then a runtime database matrix reading error occurred if the number of boxes of the changed aerodynamic model is different from the size of the saved AIC matrix. However, if you change the aerodynamic model, if the number of panels are the same, no error can be detected by the program if the number of boxes remain the same as the size of the saved AIC matrix, but the geometry is changed. Obviously, this leads to wrong solution. We're going to talk about the criterion for solution convergence at a high reduced frequency. The frequency domain unsteady pressure is oscillatory in nature. The number of waves of oscillatory pressure along the streamwise direction is proportional to the so-called compressible reduced frequency, which is reduced frequency times Mach number divided by square root of 1 minus m squared. So the high reduced frequency condition is not only based on the reduced frequency, also based on the Mach number. So apparently, when the Mach number close to 1, you have a very large compressible reduced frequency, and the aerodynamic method will have difficulty to converge unless you use a very refined panel model. And the Mach equal to 1, the number of waves is infinity. So we can use ZSAP to circumvent this problem by solving the sonic potential equation. Non-converged generalized aerodynamic forces may contaminate the aeroelastic solution. So showing here, if we use the Jordan's exact theory to compute the 2D supersonic CP at different Mach number, you can see at Mach number 2.5, you have a very smooth CP. However, when the Mach number approaches 1, then you have a highly oscillatory CP. So to capture the highly oscillatory CP. Apparently, you need a lot of core-wise buffers, and so we have a criterion built in in ASTROS ASC generator. So you will print out, if it does not satisfy this criterion, you will output a warning message to say at this reduced frequency, the panel core-wise, the core of the panel is too large. It will suggest you to reduce the panel size, and you have to use a very refined panel to obtain a converged aerodynamic solutions. And the trim flat car, you specify a mean flow condition, and this is referred to by the MK LG car. You can specify the angle tag, the beta, P ray, Q ray, R ray, and the label refers to the label of a control surface called AE Z car, and you give a value. And this, say you have elevator equal to 9 degrees, rather at 3 degrees, angle tag at 13.5 degrees.